In Euclidean space, a convex set is the region such that, for every pair of points within the region, every point on the straight line segment that joins the pair of points is also within the region. For example, a solid cube is a convex set, but anything that is hollow or has a dent in it, for example, a crescent shape, is not convex. A convex curve forms the boundary of a convex set. The notion of a convex set can be generalized to other spaces as described below. In vector spaces, let S be a vector space over the real numbers, or, more generally, some ordered field. This includes Euclidean spaces. A set C in S is said to be convex if, for all x and y in C and all t in the interval 0, 1, the point x plus I also belongs to C. In other words, every point on the line segment connecting x and y is in C. This implies that a convex set in a real or complex topological vector space is path-connected, thus connected. Furthermore, C is strictly convex if every point on the line segment connecting x and y other than the endpoints is inside the interior of C. A set C is called absolutely convex if it is convex and balanced. The convex subsets of R are simply the intervals of R. Some examples of convex subsets of the Euclidean plane are solid regular polygons, solid triangles, and intersections of solid triangles. Some examples of convex subsets of a Euclidean three-dimensional space are the Archimedean solids and the Platonic solids. The Kepler poinsot polyhedra are examples of non-convex sets. Non-convex set, concave set, redirects here. A set that is not convex is called non-convex set. A polygon that is not a convex polygon is sometimes called a concave polygon, and some sources more generally use the term concave set to mean a non-convex set, but most authorities prohibit this usage. Properties. If S is a convex set in n-dimensional space, then for any collection of R greater than 1, n-dimensional vectors U1 in S, and for any non-negative numbers lambda 1, lambda r such that lambda 1 plus lambda r equals 1, then one has a vector of this type is known as a convex combination of U1 intersections and unions. The collection of convex subsets of a vector space has the following properties. The empty set and the whole vector space are convex. The intersection of any collection of convex sets is convex. The union of a non-decreasing sequence of convex subsets is a convex set. For the preceding property of unions of non-decreasing sequences of convex sets, the restriction to nested sets is important. The union of two convex sets need not be convex. Closed convex sets are convex sets that contain all their limit points. They can be characterized as the intersections of closed half-spaces. From what has just been said, it is clear that such intersections are convex, and they will also be closed sets. To prove the converse, i.e., every convex set may be represented as such intersection, one needs the supporting hyperplane theorem in the form that for a given closed convex set C and point P outside it, there is a closed half-space H that contains C and not P. The supporting hyperplane theorem is a special case of the Hahn-Banach theorem of functional analysis. Convex sets and rectangles. Let C be a convex body in the plane. We can inscribe a rectangle R in C such that a homothetic copy R of R is circumscribed about C. The positive homo, the T ratio is at most 2 in convex wholes and Minkowski sums. Convex wholes. Every subset A of the vector space is contained within a smallest convex set, namely, the intersection of all convex sets containing A. The convex whole operator CONV equals CONV equals CONV CONV. The intersection of any collection of convex sets is itself convex, so the convex subsets of a vector space form a complete lattice. Minkowski addition in a real vector space. The Minkowski sum of two sets, S1 and S2, is defined to be the set S1 plus S2 formed by the addition of vectors element-wise from the summand sets S1 plus S2 equals X1 plus X2, X1 S1, X2 S2. More generally, the Minkowski sum of a finite family of sets Sn is the set formed by element-wise addition of vectors for Minkowski addition. The zero set, 0, containing only the zero vector 0 has special importance. For every non-empty subset S of a vector space S plus 0 equals S, in algebraic terminology, 0 is the identity element of Minkowski addition. Convex hulls of Minkowski sums. Minkowski addition behaves well with respect to the operation of taking convex hulls, as shown by the following proposition. Let S1, S2 be subsets of a real vector space. The convex hull of their Minkowski sum is the Minkowski sum of their convex hulls. CONV equals CONV plus CONV. This result holds more generally for each finite collection of non-empty sets. In mathematical terminology, the operations of Minkowski summation and of forming convex hulls are commuting operations. Minkowski sums of convex sets. The Minkowski sum of two compact convex sets is compact. The sum of a compact convex set and a closed convex set is closed. Generalizations and extensions for convexity. The notion of convexity in a Euclidean space may be generalized by modifying the definition in some or other aspects. The common name, generalized convexity, is used, because the resulting objects retain certain properties of convex sets. Star convex sets. Let C be a set in a real or complex vector space. C is star convex if there exists an x0 in C such that the line segment from x0 to any point y in C is contained in C. Hence a non-empty convex set is always star convex, but a star convex set is not always convex. Orthogonal convexity. An example of generalized convexity is orthogonal convexity. A set S in the Euclidean space is called orthogonally convex or orthoconvex if any segment parallel to any of the coordinate axes connecting 2 points of S lies totally within S. It is easy to prove that an intersection of any collection of orthoconvex sets is orthoconvex. Some other properties of convex sets are valid as well. Non-Euclidean geometry. The definition of a convex set and a convex hull extends naturally to geometries which are not Euclidean by defining the geodesically convex set to be one that contains the geodesics joining any 2 points in the set. Order topology. Convexity can be extended for a space X endowed with the order topology, using the total order less than of the space. Let Yx, the subspace Y, is a convex set of for each pair of points A, B in Y such that A less than B, the interval equals XX. A less than X less than B is contained in Y. That is, Y is convex if and only if for all A, B in Y, A less than B implies Y. Convexity spaces. The notion of convexity may be generalized to other objects, if certain properties of convexity are selected as axioms. Given a set X, a convexity over X is a collection of subsets of X satisfying the following axioms. The empty set and X are in. The intersection of any collection from is in. The union of a chain of elements of is in. The elements of are called convex sets and the pair is called a convexity space. For the ordinary convexity, the first two axioms hold, and the third one is trivial. For an alternative definition of abstract convexity, more suited to discrete geometry, see the convex geometries associated with antimatroids.